Hi folks, welcome to the Vectors and Matrices review. This isn't a review produced by IB, it's just one that I made for my students in PEI Canada. It's not a list of all the different problem types, just some of the key concepts. If you want to make the most of this, I suggest that you download the notes and print them off and do the work in advance and then use the presentation to sort of check your work. There are often a lot of different ways to work through a particular problem. If you've got a different way that you were taught, fantastic. Do that. Okay, here we go. Matrix review. You need to be able to add, subtract, multiply by a scalar, multiply matrices, find determinants of 2x2s and 3x3s without a GDC, find inverses of 2x2s without a GDC, use your GDC to do other applications, and also the big application of matrices is in solving systems of linear equations. So we'll go through these techniques. Down here I've got what's given in your formula booklet, determinant of a 2x2, inverse of a 2x2, and determinant of a 3x3. Let's try and put that to work with doing a few operations. So if I want to multiply AB, A is given up here. It's got 3 rows and 3 columns. Therefore, it's a 3x3. B has 3 rows and 1 column, so it's a 3x1. Can they be multiplied together? Absolutely. You can check by making sure that these are the same number. That means it's possible. And your resulting matrix is going to be a 3x1. Okay, so if we want to multiply them without a GDC, we're going to rewrite them. And my process is multiply across the first row and down that first column, first and only column of the second one. So we're going to have 2 times 2, that makes 4, plus negative 1 times negative 1, so that'll be 4 plus 1 now, plus 0 times 2, which is 0. So we've got 4 plus 1 plus 0. That in turn is going to give us 5 for the first entry in our matrix that is the product of these two. So 5. Now I'm going to go to my next row in the first matrix, multiply across and down. So I've got negative 3 times 2 makes negative 6. 2 times negative 1 makes negative 2, so negative 6, negative 2, and a positive 4. Negative 6, negative 2, positive 4 gives us negative 4. Okay, and finally, across and down for the last row and column, we'd have 1 times 2, 0 times negative 1, and 4 times 2. So 1 times 2 is 2, plus 0, plus 8 gives us 10. All right, the next one. We want to multiply BA. Let's see if this is possible. In this case, we'd have a 3x1, our B, multiplied by a 3x3. It just can't happen. Okay, we have different numbers on the inside here. It's not going to work. If I wrote them down and tried to multiply them, I'd be going across this first row, which only has one entry, and then down this first column. There'd be a mismatch in terms of our dimensions. I'd have a 2 times 2, and then I wouldn't know what to multiply by my negative 3. So this is not possible. All right, find det A. So you've got a formula for finding determinant of a 3x3 right up here. I've got a little shortcut, though it doesn't save that much time, that I like to use. But by all means, use the one that's in the formula booklet if you're more comfortable with that. So I'll write out the matrix A, and then I'll write out the first 2 columns again. And this will work for every 3x3. What I do first is I multiply down the diagonal, so 2 times 2 times 4 gives me 16. Down the next diagonal, negative 1 times 2 times 1 gives me negative 2. And down the next diagonal, 0 times negative 3 times 0 gives me 0. And I'm going to subtract what I get when I look at the upward diagonals. Okay? 1 times 2 times 0 is 0. 0 times 2 is 0. And finally, 4 times negative 3 times negative 1 is positive 12. Put those together, and we're going to have 14 minus 12, or a determinant of 2, which tells us that A is an invertible matrix. You can do a little proof to show that this method works for the general matrix ABC, DEF, GHK that's given in your formula booklet. Determinant of C. All right, C is a 2 by 2. Determinant of C we know is AD minus BC. If we label these as A, B, C, and D. So this will just be negative 2 times 5 minus 3 times 1. Gives us negative 13. Okay. The fact that it's not 0, again, tells us that C is invertible. Find the inverse of A. Okay, if you're asked for the inverse of a 3 by 3, it's going to be a paper 2 question. So all you need to do is put the matrix A in your GDC. And I've already done that. I've got my matrix A. So now I have to choose it and then decide to find the inverse. The GDC does all the work for me and simply copy down the answer. So don't waste a lot of time trying to do the inverse of a 3 by 3 by hand. Okay. You're not responsible for that, for the Math SL course. I should really have these lining up a little better. Negative 1, negative 2. There we go. All right, find the inverse of C. Well, the inverse of C is just going to be 1 over our determinant, okay, which was negative 13. Just by convention, I'll put the negative out here. And then we have to switch the order in our matrix of the upper left and the bottom right. So A and D switch places. I get 5 and negative 2. And switch signs on B and C. And this is given in your formula booklet. So that'll be negative 3 and negative 1. Multiply them in and we'd get negative 5/13, positive 3/13, 1/13, and 2/13. So all of this stuff is coming from what's given in your formula booklet. You definitely need to have a strong grasp of how to multiply matrices and when that is possible. All right, so now we're going to do a few matrix equations. Matrix equations work very similarly to regular equations, but we have to be careful of a few special rules. Number one, you can't divide matrices. So we've got the same matrices A, B, and C, and I want to figure out what x is in each of these. So solve each of the following equations for matrix x. Okay, well, in a regular equation, if we had x plus 2b equals something, we'd just subtract 2b from each side. Same thing in this case. So we'll have our x matrix is equal to negative 4, 3, 1, minus 2 times our matrix B, 2, negative 1, 2. Okay, so that'll be negative 4 minus 2 times 2, or negative 8. 3 minus 2 times negative 1, so that'll just give us 5. And finally, 1 minus 2 times 2, which will give us negative 3. Okay, here's where a few important distinctions start to come up in this question B. I've got ax equals b. If this were a regular equation, we'd probably want to divide by a on both sides. But that's not possible with matrices. What you can do is multiply by the inverse. And the matrix you want to get rid of and its inverse always have to go right together. So I need to pre-multiply both sides by the inverse of A in order to have A inverse and A right next to each other. And since order matters when you're multiplying matrices, I need to do the same thing on the other side. Pre-multiply each side by the inverse of A. So that'll give us x equals A inverse times B. And I can go to my GDC and get it to actually work through the operations. But the big deal here is that you could not write this as B times the inverse of A. The order or the sequence of the operations actually makes a difference here. Okay, so I've already got my A in there. And I had actually found it already, so I'm just going to multiply it here by my matrix B. And that'll give me 4, 6, and negative 0.5. Little smartboard issue there. Okay, moving on. The next one looks pretty similar. But in this case, we have XA equals this matrix that's given. Well, to get rid of the A, we're going to have to post-multiply both sides by the inverse of A. Okay, so the big deal is here, you're multiplying A inverse at the end. If you were to do that in your GDC, I won't go through the process here because it's pretty straightforward getting your GDC to actually work through this. But you should get this result. So if you've done it and you want to check your answer, here we go. All right, D, this should not take long at all. We've got Cx equals C. I'm going to want to pre-multiply both sides by the inverse of C, assuming it exists. And we know it exists because we already found its determinant, and we even found the expression for the inverse of C. So X then is going to be C inverse times C. You might be tempted here to write out the inverse of C and times it by C. But if we know that an inverse times the original matrix always gives us the identity matrix, that's going to help us out. Just like if I had 2 to the negative 1 times 2, that would give me a half times 2, or 1. The sort of equivalent to 1 in matrices is the identity matrix. And this will be a 2 by 2 identity matrix that has 1s along its main diagonal and 0s everywhere else. All right, next one. We've got 2x equals c squared. So you might be tempted to say I'm going to divide both sides by 2. Really, we should be multiplying both sides by a half to isolate x. So x is going to be a half times c squared, which would be negative 2, 3, 1, 5, all squared. Don't be that person who treats this as just squaring every entry in the matrix. You know that squaring means multiplying something by itself. So do that. Multiply the matrix C by itself. Leave the half out front until the end. It'll just make for fewer operations with fractions. And we're just going to multiply through. So negative 2 times negative 2, and then 3 times 1. We can multiply a 2 by 2 by another 2 by 2, so this works out fine. Gives us 7 for our first entry. Negative 2 times 3, and then 3 times 5 gives us 9 for our next entry. Okay, 1 times negative 2 and 5 times 1 gives us 3, and then finally 28 for our last entry. So what is x? X is 7 over 2, 9 over 2, 3 over 2, and 28 over 2, which would be 14. Okay, given that P equals this matrix that has a variable inside it, and the determinant of P is 15, find the possible values of K. And this is telling us that there should be more than one value. First thing I might want to do here is find the determinant of P. And to do that, using my little trick that I like to do, I'm going to write the matrix and then, and by the way, I didn't come up with this. And then rewrite the first two columns. Go for the downward diagonals. That'll give me 0. I'm multiplying through here. Plus 3k squared. Plus 12. Minus the sum of the upward diagonals. This would be 0. This one's going to be negative 3. and this one's going to be 6k. So det P is equal to this, which means that det P is, I have 3k squared here. I'll have a negative 6k. And I'll have a positive 15. Now we actually have to solve for k, which means we need to substitute in for det P. We knew that the determinant of P is 15, so let's put that in. 15 equals 3k squared minus 6k plus 15. Oh, it's a quadratic. Make one side 0 by subtracting 15 from both sides. Gives us 0 equals 3k squared minus 6k. Factor, greatest common factor in this case, 3k, and then k minus 2. Yes, you could have divided out the 3. Going to give us two solutions here. This is true from the zero product rule. If k is 0, then the right side will be 0. And also if k is 2. So there are two values that cause the determinant to be 15. All right, so what does the determinant determine? For a given square matrix, the determinant determines whether the matrix has an inverse. So if we find that det of some matrix A equals 0, that means there is no inverse for that matrix. Which means that we couldn't have done some of the things that we did in the previous slide using inverses, say using A inverse. In a matrix equation, det A determines whether there's a unique solution, whether you can actually do this A inverse on both sides. So here, if we find that det A equals 0, that means there's no unique solution. So there may be no solution at all, or there may be infinitely many solutions. But we certainly can't use matrix methods to find what x is. Okay, so here would be an example of using matrices in a system of linear equations. Now, it doesn't look like it's going to be a linear equation. It even starts off with a quadratic equation takes the form y equals ax squared plus bx plus c, and contains these 3 points. Then it asks us to express each of these points as equations in terms of a, b, and c. So look at this first point, -3, -4. I know it's got a y value of -4, so I should be able to sub it in this equation. Equals a times the square of my x value. Well, the x value in this case was -3. -3 squared is 9, so I've got 9a plus b times that -3, or -3b, plus c at the end. I'm going to do the same process of subbing in for my other points. So using 1, 4, that's a y value of 4. I put in 1 for x, so I get a times 1 squared, or just a, plus b times 1, or just b, plus c. Lastly, I'll do it for 528. So for a y value of 28, we're going to have a times 5 squared, or 25a, plus 5b plus c. So now we've got a system of 3 linear equations in 3 variables. Our variables aren't x and y now. They're a, b, and c. Write the information above in terms of a matrix equation px equals q. So when we have these types of matrices, typically the p is going to be our coefficient matrix. The x will be our variables matrix. And q is kind of our results, or our other side. I'm just flipping around what's on the left-hand side up here and what's on the right. So my coefficients in this first equation over here are 9, -3, and that's 1c, so a coefficient of 1. Go with my next row. I have coefficients of 1 for a, 1 for b, 1 for c. Finally, Last one, I have coefficients of 25, 5, and 1. My variables here are A, B, C. And the results were negative 4, 4, and 28. So I've got it expressed in terms of matrices. It would be kind of unpleasant for us to solve this system using elimination or substitution. You could do it. It wouldn't take that long. But the matrix methods are really nice. Right now we've got Px equals Q. Well, if we wanted to get x, or a variables matrix, on its own, we just need to pre-multiply both sides by the inverse of P. And we'll assume that that actually exists. Our calculator will tell us otherwise, if it doesn't exist. So I'll go to my GDC. I'm going to have to put in these matrices. I called them P and Q in the question. I'm going to call them D and E. So my matrix D is a 3 by 3 with the numbers 9, negative 3, 1, 1, 1, 1, and 25, 5, 1. I can go and put in my matrix E, which is a 3 by 1. And it's just sort of the y values from our original set of points. Okay, so now we're actually going to do this step over here. Multiply the inverse of P, which for me was the letter D, times the matrix Q, which for me was the letter E. And we get our nice result, 0.5, 3, and 0.5. So that tells us that A is 0.5, B is 3, and C is 0.5. In other words, a quadratic of this form goes through the 3 points that were initially specified. And you could use your GDC to check that. So systems of linear equations are one of the sort of prime applications of matrix algebra. We're going to move on to the vectors. I'm going to focus in here on sort of algebraic interpretation of vectors rather than geometric. It's not that the geometric stuff isn't important. You'd want to have a good idea of how to draw vectors. But when we're dealing with 3D vectors, generally our geometric methods break down anyway. So we'll just take a look at this in this review. Okay, when you see the letter I, it means 1 unit in the positive x direction. So I is going to be the vector 1, 0. Or if you're working in 3D, 1, 0, 0. J is 1 unit in the positive y direction, so J is 0, 1 or 0, 1, 0. And Z only exists in 3D, K rather only exists in 3D. It's 1 unit in the positive Z direction, or 0, 0, 1. So if I want to write 2i minus 3j plus 4k in vector form, here's what I can do. I can say 2i, that means 2 times 1, 0, 0, minus 3 times 0, 1, 0, because that's what j is, plus 4 times 0, 0, 1, because that's what k is. I'll put them all together. I'm going to get 2 times 1 up top, negative 3 times 1 in the middle, and 4 times 1 down below. Okay, showing all my steps. Or I just could have realized that the coefficient of I is going to be my first number. The coefficient of j is going to be my second number. And the coefficient of k will be my third number. Here's what's given in your formula booklet in terms of vectors. You've got magnitude of a vector, which just means the length of the vector. Distance between 2 points. These are eerily similar formulas. In fact, they mean essentially the same thing, just without information about direction. Or actually, there's no direction in either of them. Coordinates of the midpoint, just the average of your x's, average of your y's, average of your z's. Scalar product, or sometimes called dot product, is given here. And these are just rearrangements of the same formula. It's really applicable when you're looking for the angle between two vectors. Vector representation of a line, r equals a plus tb. So r is a vector, and represents some position. A is a vector, and it represents generally some point on the line, or an original point. T is a scalar parameter, so it's just a regular number. And then B is bold, so it's a direction or velocity vector. Okay, some things you might want to remember. For testing for perpendicularity between vectors, vectors that are perpendicular have a scalar product of 0. Their dot product is 0. And we'll put that to work for us a little bit later. Parallel vectors move in the same or opposite direction. So if I draw this vector and this vector, they're parallel. They go in the same direction. They happen to have different magnitudes. If I drew this vector, it would also be parallel to those initial two. It's going in an opposite direction, but you can see that its steepness or its slope is essentially the same. So parallel vectors have the same or opposite directions, and they're scalar multiples of each other. So if I had, say, a vector of 2, -3, and I wanted to find something that's parallel to 2, -3, a vector that's parallel, I could just take 2, -3 and multiply it by something. Say, multiply it by -3. I get this. These are parallel vectors. Or if we had taken the original one and, say, multiplied it by 2 pi, you get 4 pi and -6 pi. Still parallel. Let's take a look at some vector basics here. So if I have points P at -3, 2, 4 and Q at 1, -1, 0, and I want to find the vector PQ, what I'm going to need to do is take the coordinates of Q, my terminating or final point, and subtract off the coordinates of P, which would be my starting or emanating point. And that'll give us a vector PQ that goes 4, -3, and -4. Hard for me to draw that in 3D. Finding magnitudes would be another basic skill that you need to make sure you can do. So we've got this vector A here, and when we see these absolute value type signs, they mean magnitude. So our magnitude formula told us it's the square of the first number in your vector plus the square of the second number plus the square of the third number. And we're square rooting the whole thing. It comes straight from Pythagorean theorem. So we'd get 16 plus 9 plus 16, or root 41 exactly. All right. The vector B is perpendicular to A. So what does that mean? Well, it means, let's check what we found on the last slide. Recall that perpendicular vectors have a scalar product of 0. So if these are perpendicular, then they're scalar product or dot product equals 0. And there's a good chance that writing A dot B equals 0 will get you M1 on a question like this. Okay, no guarantees, but depending on the mark scheme, well might. So A dot B just means 4, negative 3, negative 4, and the scalar product of 2, m, and negative 7. That's equal to 0. So all I do is multiply the top lines by each other. 4 times 2 is 8. Middle lines, negative 3 times m is negative 3m. And negative 4 times negative 7 for the last line would give us positive 28 equals 0. Work that out. We get negative 3m equals negative 36. Divide both sides by negative 3. And we're going to get m equals 12. You could plug that back in and just verify that it actually does give you a scalar product of 0. But assuming we've solved it properly and have done everything right with our equation, it should work out. Okay, the vector c is parallel to a. Parallel vectors. We said that they're scalar multiples of each other. So that's telling us that if I multiplied my original vector a, which is 4, negative 3, negative 4, by some constant, I would get this new vector, negative 6, and 6, which is going in the same or an opposite direction, meaning they're parallel. Now, if I look at this just straight from vector methods, it's going to be hard for me to solve because it seems like I have one equation and I have two variables. But if I look at the parametric equations that come out of each row, it's pretty nice. I actually have 3 different equations and only 2 variables. So from the first row, I'd have 4k equals negative 6, which would give us k equals negative 3 over 2. The second row will give me negative 3k equals n. Oh, no problem. We can just substitute in for k. Negative 3 times negative 3 over 2 equals n, or n equals 9 over 2. Now you might say, well, was it necessary for us to use those specific 2 rows? No, it's not. If you had chosen to start with the third row of negative 4k equals 6, you also would have gotten k equals negative 3 over 2. You wouldn't have been able to start with the middle row because it would have had 2 variables in it, though. Find the angle between A and D to the nearest degree. Okay, and A, recall, was 4, negative 3, negative 4. Here's what we need to use. From our formula booklet, angle between 2 vectors. And they're nicely labeled here. You know, if you're not quite sure, just go to the vector section of your formula booklet and look for the headings. Angle between 2 vectors, there it is. Now this means just dot product of v and w. So for us, we just happen to be using different letters. We're going to have cos theta is the dot product of our 2 vectors that we're interested in over the magnitude of A and the magnitude of D. Which means we've got to find a few things. We already know that the magnitude of A is root 41. We better find the magnitude of D, which would be the square root of 2 squared plus negative 1 all squared plus 2 squared. That'll be 4 plus 1 plus 4, or the square root of 9, which is just 3. Last thing we need to find is A dot D. That just means top line times top line, 4 times 2, plus middle row times middle row, negative 3 times negative 1, plus bottom times bottom. Okay, if we work that out, we'll get 8 plus 3 minus 8, or a dot product just of 3. Now I've got all the pieces that I need to substitute in. So I can say that cos of theta is equal to A dot D, that's 3, over mag A, mag D. I just reversed the order there, so I put my regular number out front. I can simplify if I want to 1 over root 41. And then to actually find the angle theta, I'm going to need to use arc cos, or inverse cosine, of 1 over root 41. The question says to the nearest degree, so that's making me think, oh, I probably better put it in degree mode. Okay, and I need to find the inverse cos of 1 divided by the square root of 41. Gives me 81 degrees. All right, vector equations of lines. So they take this form, r equals a plus t times b. Notice that t is the only one there that's not bold. T is just a scalar. The rest of them are vectors. So a is some known point on the line. B is your direction vector. And that's really important. You can tell your direction vector in these equations because they've got the scalar right next to them. So it's of this form, tb. T is some scalar parameter. It's often time. And r is the position on the line with given a, b, and t values. When you want to compare lines for different properties, whether it be perpendicularity, parallelism, or angles formed between lines, so say I've got these two lines, I'm comparing the directions in which they're moving. So I'm always going to be comparing this direction vector b. Let's take a look at what Alberto is up to here. Traveling in a glider in the direction 2, 2, negative 1 at 6 meters per second. Find the velocity vector of the glider b. Now you might think, I've already got that. I know which way he's moving. You know the direction that he's moving, but not necessarily the velocity. Not necessarily the velocity. What we need to know is the speed that he's traveling at if he's using this vector. And speed is simply the magnitude of velocity. Speed is mag of velocity. Okay, and the magnitude of this vector would be 2 squared plus 2 squared plus negative 1 squared, square rooting the whole thing. That'd give us 3. So this direction vector that we were given to start with is not actually the velocity vector. It's too small. It only represents 3 meters per second. Our velocity vector has to be twice as big, or 2 times the direction vector. Has to go in the same direction, but have the right magnitude. So that'll give us 4, 4, negative 2. When t equals 0, Alberto has a position of 19, negative 12, 20. Hence, write a vector equation in the form, that should be a non-bolded t, for the position of the glider after t seconds. So all we want to know is, where is Alberto after t seconds? He starts off at the initial point, 19, negative 12, 20. So that's going to be the first vector that I write down. Plus t times his velocity vector, which we just found was 4, 4, negative 2. Okay. So this is initial point, and this is velocity vector. The glider passes through this point D, 39, P, and 10. Find the value of P. So we know that after a certain amount of time, he ends up at this point, 39, P, and 10. And his position is given by the equation that we just found. Okay, this isn't looking very promising to start off with, but once again, if we look at the parametric equations that come from each of the rows, From the first row, I'd have 39 equals 19 plus 4t. If I solve that, subtract 19 from both sides, I get 20, divide by 4. That'll give me t equals 5. The middle line, p equals negative 12 plus 4t. Oh, but we know that t now is 5. So p should be negative 12 plus 20, or 8. Again, you could have started with the last line and had 10 equals 20 minus 2t. That also would have given you t equals 5. And if it hadn't, then the glider would never pass through this point. Okay? If we'd gotten different t values depending on the line or the parametric equation we chose, that would be a bad situation. It would just show that the glider never passes through this point D. Is never at once at an x value of 39 and a z of 10. D, the position of a balloon. So another object is given by this. 19, 12, and 2 plus s by 5, negative 1, and 2. Okay? And it passes through the point D. So at some point, or at some time, it's going to go through 39. We found P was 8 and 10. So I'm just using this point D from up here. Again, we can set up parametric equations here. We're going to get 39 equals 19 plus 5s. That we can solve. We'll get 20 equals 5s, or s equals 4. Sorry, this is coming from the first line, the first parametric equation. At this point, we haven't quite shown that the balloon passes through D. We've shown that it works for our x values. We have two options here. You can solve for the other two parametric equations and show that they also have solutions of 4. Or you can plug in 4 for s and see what point you get. Now let's see. This would be 19 plus 4 times 5. That's 39. 12 plus 4 times negative 1. That would be 8. And 2 plus 4 times 2. That's 10. Eureka! We actually do pass through this point D. That was 39, 8, and 10. Okay. Calculate the acute angle formed between the path of the balloon and the path of the glider when they meet at D. So since these are lines in space that continue on in infinity in either direction, we're going to really have two angles that are formed whenever we meet. We'd have this one here and this one here. It's telling us in this case that we want the value of the acute angle. So if we want to compare the angles formed when they meet, we need to compare what kind of vectors? The direction vectors. Okay, that's what we started off with up here when comparing lines for perpendicularity, parallelism, or angles formed between the lines, comparing direction vectors or velocity vectors. Close cousins. So for Alberto, the direction vector that we'd be talking about, or velocity vector, would be 4, 4, negative 2. You could also have used 2, 2, negative 1, the initial direction. For the balloon, the direction vector, I'm going to call it, I don't know, I'll call it Q, is 5, negative 1, 2. It's this one right here. I know if I want to find the angle between them, I have to look at the dot product. So B dot Q over mag B, mag Q. This is angle between vectors given to you in your formula booklet. So I'm going to need to find the magnitude of B, which I actually already know is 6, because it represents 6 meters per second. The magnitude of Q, which is going to be the square root of 5 squared plus negative 1 squared plus 2 squared, or root 30. And I also need to find the scalar product or dot product of the two. B dot Q is going to be 4 times 5 plus 4 times negative 1 plus negative 2 times 2. Okay, work that out, and I'm going to get 12. Sub it in. We have cos theta is going to be b dot q, that was 12, all over magnitude of b times magnitude of q, or 6 root 30. So cos theta, if we wanted to simplify a little bit, is 2 over root 30. The angle itself is going to be the inverse cos, or arc cos, of 2 over root 30. It doesn't specify here whether we're talking about degrees or radians, so they should accept the answer either way. 2 divided by root 30. My calculator's still in degree mode. It gives me 68.6 degrees, which is an acute angle. Or, if we had done this in radians, this would just be times pi divided by 180, 1.20 radians. The last page of this review, sorry, a little smartboard issue here, 1.20 radians. Last page of the review is just a set of different formulas that are given to you for 2D and for 3D. They're given to you only in terms of 3D in your formula booklet, and not every one of these is given in your formula booklet. So just if you are having trouble figuring out what to do in 2 dimensions, here they are on the left column, and in 3 dimensions on the right column. Okay. Vector from O, meaning the origin, to A, is just going to be the x-coordinate of A and the y-coordinate of A. We've got formulas here for finding the vector AB. It's always the x-coordinate of B minus the x-coordinate of A, y-coordinate of B minus the y-coordinate of A. So always final minus initial, or B minus A. Magnitude comes straight from Pythagorean theorem. Vectors are parallel if A equals KB. There's scalar product of A and B. And we should say here, vectors are perpendicular. So what one of the good things that scalar product does is lets you test for perpendicularity really easily and quickly. If you find that the dot product of 2 vectors is 0, they must be perpendicular. Folks, good luck on your Math SL exams. See you for another review.